Hello, welcome to Econometrics Melody. In this video, we'll discuss about the beta distribution. First of all, let us see some of the useful functions. Exponential and logarithm are inverse to each other. That is why we get the value of factorial in this case and the value of gamma in this case. And we want to show that gamma n is equals to n minus 1 factorial by this example. So gamma 6 is equals to 5 factorial, gamma 12 is equals to 11 factorial. We cannot calculate the factorial of decimal numbers while we can calculate its gamma value. Now let us see some of the formulae of the beta distribution, and in our next session we will calculate the PDF and CDF of the beta distribution. First of all, let us see about the mean. Mean is equals to A divided by A plus B. Both A and B are the same parameters, and its variance is equals to AB divided by A plus B plus 1 into A plus B square, and this can be expressed in terms of mu because A divided by A plus B, A divided by A plus B is equals to mu. So this can be written as mu divided by A plus B plus 1 and into A plus B. The PDF of the beta distribution, it is expressed as x to the power A minus 1, 1 minus x to the power B minus 1 divided by gamma A into gamma B divided by gamma A plus B. This much gamma A into gamma B divided by gamma A plus B. This is what we mean by the complete beta function, and we get complete beta function when we integrate from 0 to 1 and t to the power A minus 1, 1 minus t to the power B minus 1 when we integrate it with respect to t. Similarly, the CDF of the beta distribution, it is actually a regularized incomplete beta function. So when we divide the incomplete beta function by the complete beta function, that is what we mean by regularized incomplete beta function, and this term is our complete beta function. So when we divide the incomplete beta function by the beta function, we get the CDF, and this is incomplete because we integrate it from 0 to x only. So if we integrate it from 0 to 1, it is complete beta function. So that is why we call this above numerator is incomplete beta function, and we integrate from 0 to x, t to the power A minus 1, 1 minus t to the power B minus 1, and we integrate it with respect to change in t. So we'll calculate it by the help of integration, and we'll show it in our example. Now let us see what is our gamma function. Gamma function is again the integration from 0 to infinity, and for this parameter z, we take t to the power z minus 1, e to the power minus t, and we integrate it with respect to change in t, which for the gamma z is equals to z minus 1 factor, which we have seen in our earlier example, and this can again be written as z minus 1 into gamma z minus 1. Now let us calculate the CDF and PDF of the beta distribution. We'll calculate the CDF of beta distribution for these three examples over here, and we will use the quadrature class in Mata, and let us calculate it. And I'm going to use Stata version 17 for that. The quadrature class is supported from Stata 16 onwards. So the first example, we take our parameters, say parameter A and B is 3 and 6 respectively, and for the value of x to be 0.3, and in beta function the value of x ranges between 0 to 1, and this is our incomplete beta function, x to the power A minus 1 into x 1 minus x to the power B minus 1, and we integrate it from 0 to x, and where x is less than 1, it is 0.3 in between 0 to 1. Now let us see what is the value of lower incomplete beta function. So this is the value of lower incomplete beta function, and to this incomplete beta function we divide it by the complete beta function, and that is what we get is the regularized incomplete beta function. And this complete beta function can be expressed in terms of gamma is gamma A plus gamma B minus gamma A plus B. Now let us see whether we, and I beta, it is the Stata function to calculate the CDF of beta distribution. And for the parameters, this parameter A and B, 3 and 6, and the value of x is 0.3. So what is the probability of getting 0.3 or less than 0.3? Now let us see, both of them should yield the same result. It is 44%. For x to be 0.3, it is 44%. Now let us see it by the help of the graph. 0.3 or less, it is 44%, and somewhere over here. Now let us see another example, and we take, this time we are going to take the beta parameter, and this time we are going to take the value of, say, parameters A and B is 6 and 9, and for the value of x is 0.6. Now we have substituted the value of A, x to the power A minus 1 into 1 minus x to the power B minus 1. Then after, this is our function, and we integrate it from 0 to x, and let us see what is our lower incomplete beta function. So the value of lower incomplete beta function, it is this value, and we have taken the same value as the lower incomplete beta function, and we have divided it by the complete beta function, and let us see, both of them should yield the same result, and it is 94%. So the probability of getting less than 0.6, less than equal to 0.6, it is 94%. Less than 0.6, it is 94%, somewhere over here. Now let us see another example, and the shape parameters a and b, they are equal in this case, and we have taken it to be 12, and for the value of x to be 0.5. So we have set the value of a and b is 12, and then we integrate it from 0 to 0.5. And let us see what is the value of our lower incomplete beta function for these parameters, and it is this value which we have taken over here as well, and divided by the complete beta function. Incomplete beta function divided by the complete beta function, it is our CDF of the beta distribution. And we have the Stata function to calculate the same. Let us see, both of them should yield the same result. It is 50%. So the probability of getting less than equal to 0.5, it is 50%. Let us check it by the help of the graph as well, CDF graph. So 0.5, it is 50%, somewhere over here. Now let us see some of the examples of the PDF of beta distribution. So beta den, this is the Stata function to calculate the PDF of the beta distribution for the parameters a and b, and for the desired value of x. And this is the generic formula. So it is x to the power a minus 1 into 1 minus x to the power b minus 1 divided by the complete beta function expressed in terms of gamma here. Now let us see, both of them should yield the same result. It is 23%. So the probability of x to be 0.25, it is 23%. And let us see it in PDF graph as well. So 25, and it is some percentage in between 16 to 33. So what was it? It was 23%. Now let us see another example where our parameter a is 7 and b is 2. So for the value of x is 0.75. Both of the formula, they should yield the same result, and it is 2.49. So the probability of x being exactly 0.75 is 2.49, 2.49, and a 0.5, 0.75, I guess, and it is 2.49. We're over here. Now let us see another example. This time we are taking the shape parameters to be equal, and that is 9, and for the value of x to be 0.5. Both of the Stata function as well as its generic formula, it should yield the same result. It is 3.33, and 0.5, it is 3.33. So here it is 0.5 over here, and it is 3.33. Now let us play around with the PDF for different parameters. Here the parameters a and b are 0.2 and 0.3 respectively. We get this kind of graph. Similarly, for another parameters 0.5 and 0.5, we should get this kind of graph. And when a and b are equal to 1, let us see, we get this kind of graph. And when the value of a and b are 2 and 1 respectively, we get this kind of graph. And again, when the value of a and b are equal and 2, let us see, it is this kind of graph. And for the value of a is 1 and b is 4, b is greater, so we should get some sort of a decreasing kind of graph function. And let us see, when they are equal, we should get some sort of bell curve, nearly some sort of bell curve. And again, when they are equal, but this time a bit greater, so b is 4, a and b, they are 4, so nearly it is going to take the shape of the bell curve. And let us see, and when a and b are both equal to 15, we get this kind of graph, bit bell curved. Now let us run some of the simulations, and this time we are going to increase the parameter a, the shape parameter a, from 1 to 10, while the b parameter, it is going to be 0.3. And let us see what kind of graph do we get. And let us repeat the same process. Increase the a parameter from 1 to 10, and while the value of b parameter, it is 1, and we get this kind of graph. And let us increase the value of a from 3 to 12, and the b parameter is 2. We get this kind of graph. Similarly, let us change the b parameter, and when the a parameter increases from 3 to 12 and b parameter is 3. And let us now change the a parameter from 10 to 18, while our b parameter is going to be 9. Now let us see what kind of beta distribution do we get when we change the b parameter for constant a. Here a is 0.3 and b parameter is going to change from 1 to 10. Let us repeat the process, and for the a parameter to be 1 and b parameter is going to change from 1 to 10. And this time for the a parameter to be 2 and the b parameter is going to increase from 3 to 12. And let us increase the a parameter from 2 to 3 and the b parameter is going to increase from 3 to 12. Now for a is equals to 9, let us increase the b parameter from 10 to 18. Now let us say another simulation, and this time we're going to keep both the a and b parameter to be equal, and we want to show that is the both parameters are equal, we get some sort of bell curve. Now let us increase the value of a and b from 5 to 15, and both of them will be equal. So for the higher equal value of a and b, we get more of a bell-shaped curve. So the domain of beta distribution is actually from 0 to 1 at the interval of 0 to 1. Now let us see a program called beta area. Econometrics Melody has written it, and this is useful for the hypothesis testing. So the shape parameter a and b are the value of shape parameter a and b are 3 and 1 respectively, and we want to test the hypothesis whether the value of x is less than 0. This is our null hypothesis. X is equals to 0.3. It is our null hypothesis, while the alternative hypothesis x is less than 0.3 or x is greater than 0.3. For the right tail test, our p-value it is 97%, which is quite greater than our significance level of 5%. That is why we fail to reject the null in this case. While our left tail test, x is less than 0.3, the p-value is 2%, or let us call it 3%, and which is less than our alpha value. And that is why we reject the null in this case, and we conclude that the value of x is in fact less than 0.3. And at the backdrop, we have a normal distribution with the mean and variance equal to the mean and variance of this beta distribution. Now let us manipulate both the shape parameters, and the value of a is 6, value of b is 3, and we want to test the null hypothesis whether the value of x is 0.35. Our null hypothesis x is 0.35, and our two alternative hypotheses x is less than 0.35 either, or x is greater than 0.35. So for this left tail test, the probability is, or the p-value is 3%. So we reject the null in this case. In other words, we say that we don't belong to this null region because it is only 2.5%, that is 3%, and this 3% cannot explain the features of this null distribution. That is why we reject the null, and we conclude that the value of x is less than 0.35. While for the right tail test, our p-value is 97%, and which is greater than our alpha value. That is why we fail to reject the null in this case, and we conclude that the value of x is 0.35. Now let us see if a process follows a beta distribution and its shape parameters are 3 and 3 respectively. The shape parameters are equal, and we want to test a hypothesis whether the value of x is 0.85. So our null hypothesis x is equals to 0.85, and two alternative hypotheses x is less than 0.85 or x is greater than 0.85. So for our left tail test, the p-value is quite greater than our alpha value of either 5% or 1%. So we fail to reject the null in this case. In other words, we are saying that this belongs to this null region. Now let us see our right tail test. For the x is greater than 0.85, our p-value is 3%. So again, our p-value is less than our alpha value. That is why we reject the null if our alpha value is 5%, and we conclude that the value of x is greater than 0.85. But if we take our alpha value as 1%, then our p-value is greater than our alpha value, and we fail to reject the null in this case, and we conclude that the value of x is 0.85. Now let us see if a process follows a beta distribution and the parameters are 0.9 and 3 respectively, and we want to test our hypothesis whether the value of x is 0.5. So our null hypothesis x is 0.5 and our alternative hypothesis x is less than 0.5 and x is greater than 0.5. So in both of the cases we see that our p-value is greater than our alpha value of either 1% or 5%. So that is why we fail to reject the null in this case, and we conclude that the value of x is in fact 0.5. Again, the beta distribution is defined within the interval of 0 and 1. Now let us see some of the uses of the beta distribution, and I have collected it from different sources. Beta distribution is often used to model the probability of success in a binomial experiment where the parameters of the distribution are chosen to represent the prior belief about the probability of success. The beta distribution is a conjugate prior for the binomial, negative binomial, and geometric distributions, which means that if the prior is a beta distribution, the posterior will always be a beta distribution. The beta distribution can also be used to model continuous variables that are constrained to lie between 0 and 1, such as the proportion of time a machine is operating correctly. It is also used as a prior distribution on the parameters of the linear regression model when the response variable is a proportion of or a rate. It is commonly used as a prior in Bayesian multi-armed bandit problem, where it is used to model the probability of success of different arms. In image processing, the beta distribution is used to model the intensity of pixels in an image. The beta distribution is used in robotics for tasks such as object grasping, where it is used to model the probability of success of different grasping strategies. The beta distribution is used in economics to model various types of financial risks such as credit risks, market risks, and operational risks. The beta distribution is used in survival analysis to model the probability of survival beyond a certain time. And beta distribution is used in many other fields. So this is it for this tutorial. Thank you very much for your time. Thank you very much, Econometrics Melody.